Hello everyone. The papers we will discuss today are the European Roadmap towards fusion electricity. Chapter 5. Neutron-tolerant materials. The neutrons generated by the fusion reactions interact with the material structures surrounding the plasma. Largely, this is desirable as the neutrons need to produce the tritium in the breeding blankets and also to generate the heat driving the electricity generating turbines. However, the neutrons will also displace atoms in any structure close to the plasma. In ether, every one atom in the plasma-facing materials will undergo, on average, typical 1 to 2 displacement expressed in dPa displacement per atom. The materials in ether are designed to cope with these loads. Demo will have neutron loads that are in the order of approximately 20 dPa during the first phase, when it is operated with a starter blanket, and about 50 dPa in a later phase. It is not so much the neutron flux, but the neutron fluence due to the longer pulses that leads higher dPa level. Materials that can be used in the first phase of demo already exist. They have been tested and validated in materials test reactors. For the full qualification, they need to be further tested and validated in a fusion-relevant neutron spectrum. Materials for the later phase of demo still need to be developed, or at least improved with respect to the present materials. In Euro, the fusion materials research strongly concentrates on a limited number of main materials. Euro-FAR are reduced activation ferritic martensic steel array. For the structural components, tungsten for the plasma-facing components, and CuCrZr for the components aimed at removing most of the power deposited in the plasma-facing structures. An issue is that many of the materials suffer from embrittlement at low temperatures, while the mechanical strength deteriorates at too high a temperature. Therefore, much work is being devoted to widening the operational window of the materials. A relatively recent success is the widening of the operational window of Euro-FAR 9722 by applying specific non-standard heat treatments for cooling materials. An important issue is the loss of mechanical strength of CuCrZr above 300 degrees under irradiation. Much attention is devoted to reinforcement strategies to extend the use of materials from ether to the much more demanding demo operating conditions. Good progress has been reported with fibre reinforced CuCrZr pips, in which tungsten wires are braided and then embedded in the array by melt infiltration. For the validation and qualification of materials to be used in a fusion reactor, irradiations campaignings in test reactors are being executed and need to be continued in the coming decade. The ultimate testing and validation should be done with a source featuring a fusion-relevant neutron spectrum. Such a source is the IFMIF, or the dons, both neutron sources are based on a deuterium-ion accelerator directed towards a liquid lithium target. Where the lithium nuclear reaction will yield a neutron spectrum that is reminiscent of that of a fusion reactor. The main difference between IFMIF and DONES is that IFMIF has two accelerators, whereas DONES has only one. The design of DONES is presently ongoing, and construction should start early in the next decade. The preferred site in Europe is near Granada in Spain. The neutron wall loss is an important measure of the severity of the operational environment for the first wall and blanket. Higher loads need more cooling, which has an adverse effect on the tritium breeding ratio. Additionally, there are strong limitations arising from available fusion nuclear guide structure materials that can withstand loads above typically 20 dps still have to be developed, tested, and qualified. Typically, 30 years are needed from the early development of a material until the final qualification necessary to obtain the nuclear license. Thanks for listening to the end of today's show.